This is part 2 of hyperbolas. Hopefully, if you're watching this, you've just watched part 1 of the hyperbola video series. In this video, we're going to look at asymptotes and make some sense of these crazy things. If you remember back to graphing stuff in like trigonometry or something like that, when you graph stuff, you have asymptotes, and even with rational functions and stuff like that. But anyway, asymptotes are basically guidelines where graphs are going to get close to but never really touch, right? And in this case, the asymptotes are going to sort of crisscross at the center of a hyperbola, and they're going to guide the way that our hyperbola is shaped. Sometimes it'll look like that, but sometimes it'll look like this, and that really depends on what the b value is and what the a value is in the relationship between the two. And the asymptotes are quite simply just they're just diagonal lines, and linear equations, of course, are y equals mx plus b. And in this case, if the hyperbola itself is horizontal, so we have the transverse axis this way, then that means that we're going to go b over a. If the hyperbola is vertical, that means we're going to go a over b. That's really the only difference. And you can see h and k are in there as well. Here's a pretty good picture of what we're talking about, right? The asymptote itself is this dotted line right here and right here. They're basically going to have opposite slopes as each other. Otherwise, they're going to be the same, but they're kind of sort of being guided by this sort of box, this little rectangle. And that rectangle is sort of like, between the conjugate axis, which is this right here, that's like the minor axis, and this distance right here between the vertices. So we're going to take a look at all this stuff and graph some asymptotes, write the equations of some asymptotes, and make some sense of this. This is kind of a crazy thing, but if we get some practice, hopefully you'll see that it's not too tough. Number 2, this is actually the first example today in this video, but example 2 overall, because this is a continuation of the last video. So first thing we're going to do is, when we see a hyperbola, you're going to notice there's a minus sign in the middle, and if there's ever a number over here that is not 1, you want to just get it to be 1. So let's divide everything by that number, and we did this for the ellipse as well. So that's x squared, I'll put it over here, x squared over 4 minus y squared over 16 equals 1. Now in hyperbolas, you always have the a squared term here and the b squared term here. The numerators are the things that change in the hyperbola equation, but the a and the b are always in this order. So that tells me that lowercase a is 2 and lowercase b is 4. If a squared is 4, a is 2. If b squared is 16, b is 4. So that means we need to find c, and to find c, we just use this really cool relationship. So it's 2 squared plus 4 squared equals c squared. 4 plus 16 equals c squared. So c squared is 20, which means c is the square root of 20. If c is the square root of 20, let's break that down. We'll simplify this. 4 and 5, break them up. The square root of 4 is 2, radical 5. So I'm going to write it like that. And just as a sort of a recap here, a is the distance from the center to the vertices. B is the distance, this is all in the first part of the video if you want to go back and watch that, distance from the center to the endpoints of the conjugate axis. And that's really the big one that we're going to look at today. We didn't really spend too much time talking about B in the first video, but we certainly will in this one. And C is the distance from the center to the foci. Alright, so those three things are really important to know. It's also important to know this relationship. It's different for an ellipse and a hyperbola, so just be careful with that. You know, on your tests, hopefully you have formula sheets, but if not, you know, you just got to memorize this stuff, and the best way to memorize isn't just to commit it to memory, but to use it, and use it over and over and over again. And the more that you use stuff, the more you memorize it. Alright, so next up, let's talk about what our center is. Our center is always going to be determined by our numerators. In this case, I don't see any parentheses at all. So that leads me to believe that my center is at 0, 0. So I'm going to put that on my graph as my center. A is the distance from the center to the vertices, but we need to know which way to go. Do we go up, or do we go up and down, or do we go left and right? And that is determined by whatever letter leads the fraction, or the left side of the equation, if you will. So if it leads with x, if x is the lead numerator, that means our transverse axis is horizontal. Our transverse is our major axis. The transverse axis is going to be horizontal. So if the transverse axis is horizontal, that means our vertices will go left and right. So I'm going to put my vertices 2 units to the right and 2 units to the left. That's our vertex, and that's our vertex. The foci are 2 radical 5 units to the left and right as well. So let's put those in there too. I'll put those in maybe like an orange or something. And 2 radical 5 is, you know, it's the same as the square root of 20. So if you want to kind of think about what that is in terms of like a decimal, it might be helpful. And we can sort of ballpark that. We don't have to use a calculator. You can, but think about it. We know the square root of 16 is 4, and we know the square root of 25 is 5. So 20 is 4 units away from 16 and 5 away from 20. So this thing is going to be, this number, the square root of 20 is between 4 and 5, and it's slightly closer to 4. So I'll say it's about 4.4. I literally don't know what it is, but I'm going to guess it's around 4.4. If I'm wrong, then so be it. But I'm going to put that right there and right there. Cool. So those are our foci, right? So I'll put the F for focus in both cases. And this letter B tells us the distance from the center to the endpoints of the conjugate axis. So we need to go up 4 and down 4. So right here and right here. Okay. So this is kind of working out to be hopefully a pretty easy thing. What I want to do now is draw a sort of an imaginary little box here. And the box is going to be formed from the vertices and the green dots. Alright, so that's kind of like a nice little imaginary box. And what that's going to do for us is provide us with a point right here, 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 and here that will guide our asymptotes. In other words, the asymptotes are going to go from the center to this point. So I'll draw that as a dotted line. And it'll go from the center to this point, and it'll keep going. You can extend it. And just do your best to keep these somewhat straight. and they'll extend down this way as well. These are guidelines for our parabola, or excuse me, for our hyperbola. And if you notice in the first video, we didn't really spend too much time on this. We didn't spend any time on this because I just wanted to get the basics down. But now that we have the basics down, and we can really get an idea of how to shape this, how to shape these branches of our hyperbola. So what you're looking at here is, and maybe I'll get rid of that box. It's a little bit visually confusing. What you're looking at here is how we are going to shape this hyperbola. So let's do that. Let's literally just draw that in there. I'll use a black color for this. It's going to go through the vertex, and it's going to sort of infinitely approach. Maybe that's not so good, but it's going to infinitely approach these asymptotes. So what you want to do is get your hyperbola to go through the vertex and sort of infinitely approach each asymptote. And this is probably easier for you guys to do on actual paper. It's not so easy for me to do on this computer, but I'll do my best. So you can see that this hyperbola isn't shaped like this really at all. It's more like sort of wide open and sort of tall. And we know that because of these asymptotes. They're telling us exactly how to shape our hyperbola. So maybe I'll highlight these asymptotes here, and we'll try to write the equation of them as well. Before we write the equation of the asymptotes though, let's just get some of the basic stuff out of the way. We got the center. Let's see if we can write the vertices coordinates and the foci as well. The vertices are, let's see, -2, 0, and 2, 0. And the foci are C units away from our center, so it's 2 root 5 comma 0 and -2 root 5 comma 0. And those green points, if you were ever asked for those, it would be 0 comma 4 and 0 comma -4. Okay. The asymptotes themselves have equations. The equation for an asymptote is, in this case, given by this equation, right? It's b over a because that is rise over run. This is the slope of our linear equation. Rise over run is going to be, I mean, think about this. It's going to be up. Let me use a different color here. Let me use maybe pink or something. So we're going to go up, and that is b units. The distance from the center to that green point is b units. So that's the rise over run. Run in this case is the distance from the center to the vertex, which is a. So that's why we get b over a. I'll leave that there for you. B over a. And in this case, b is 4 and a is 2. So I'll put those in there. We get y is equal to k plus or minus 4 over 2, x minus h. H and k come from the center. In this case, the center is 0, 0, so those are just going to disappear. So we get plus and minus 2x. Those are the equations of both of our asymptotes. In other words, one of them is 2x and the other one is -2x. If you want to combine them into one, you just say plus or minus 2x. So there you go. I think that about does it for example number 2. There's a lot going on, and we're going to look at one here. In the next exercise, I'll let you try it on your own. That will do all this same stuff, but this time you'll see that the hyperbola is shaped a little bit differently. So go ahead and try this one on your own and see if you can come up with where the foci are and all that stuff. So go ahead. Okay, here we go. You notice I changed the graph a little bit. I actually wanted a different coordinate plane on there, so I changed that for us. But hopefully you tried that on your own. You know, as I said in the past couple videos, the best way to learn how to do this stuff after you've been taught how to do it is to actually just practice. So the first thing we want to do is divide everything by 36. So let's go ahead and divide all terms by 36. We want to get that right hand side to be a 1. 4 over 36 is 1 over 9, minus x squared over 4 is equal to 1. So that leads me to believe that my a term is 3 and my b term is 2. Remember, in a hyperbola, the a term is always leading off. It's always in the denominator of the first fraction. The fact that y is in the numerator of the first fraction tells me that this is a vertical transverse, did I spell that right? I think so. Transverse axis. In other words, this hyperbola is up and down. So we'll keep that in mind as we go along here. The center is easy again. There's no really h or k in parentheses, so it's just 0, 0. The a term is 3, the b term is 2, the c term is given by this relationship, so c squared is equal to 9 plus 4, so c is root 13. Can't simplify that, so we'll just leave it like that. Root 13 is a little bit less than 4, so I'll call it about 3.6 or so, just for our reference. It's approximately equal to 3.6. And I think we're ready to start graphing some stuff. So let's put our center at 0, 0. We know this is a vertical hyperbola, so the a term is going to lead us up and down to the vertices. The vertices are at positive 3 and negative 3. The foci are going on that same vertical transverse axis, up 3.6 and down 3.6. I'll put those in, I don't know, orange or so. So that'll be right around here and right around here. The b term is 2. That'll lead us left and right. These are the endpoints of our conjugate axis. And again, maybe I'll draw that little box where we have going from the vertices through these green points. This is like an imaginary rectangle, and that'll leave us with points at the corners that the asymptotes are going to go through. So let's go ahead and draw these asymptotes, and we'll see if we can't shape this hyperbola. And again, it's probably a lot easier for you guys to use your straight edges to draw these things. Mine aren't super straight because I'm on a computer tablet here. It's a little bit tricky, but I don't think it's too terrible. Those are our asymptotes. This is what's going to shape our hyperbola. So it's going to go through the vertex, shape towards each asymptote, and kind of wrapping around the focus. So let's see how I can do with this. Not too bad. I'll put arrows on the ends. Down here, again through the vertex. Not too bad. Alright, cool. And just for good measure, just to stay consistent here, let me get my bigger highlighter out. Maybe I'll highlight those asymptotes again, just to give you an idea of just exactly how we shaped our hyperbola. Cool. So those are the imaginary boundaries that the hyperbola is never going to touch. It tells us exactly how wide to make our hyperbola. Let's see. Let's get some coordinates out of the way. The vertices are in blue, so those are going to be negative or 0, 3, and 0, negative 3. The foci are up and down root 13. That's negative, sorry. And next up would be the, I guess, the asymptotes. The asymptotes, we need equations for those. So the equations for an asymptote are, in this case, it's plus or minus a over b. Now the reason it's different is because, think about it, this distance now from the vertex to the center, that's a. That's going to be our rise, and our run is from here to here, that's b. So that's the, you know, in the case of a vertical transverse axis, your slope is a over b. So just be careful with that. H and k are still 0, so the asymptotes are going to be y is equal to plus or minus a, which is 3, b, which is 2, and then the x is there. So there you go. Hopefully that helped you out. This was our focus on asymptotes. Notice that these two examples were just when the center was at the origin, so you know, it's a good place to start. In the next video, we're going to move our center a little bit, which really changes this h and k and kind of makes things a little bit more complicated. But you know, hyperbolas are, if you can really kind of make sense of the ellipse, you can probably make sense of the hyperbola. The hyperbola just has a few nuanced differences, and of course these asymptotes are way different. But hopefully this helped you, and as always, you know, please subscribe. If you have any questions, just shoot me a comment and I'll get back to you. In part 3, we'll look at some more complicated examples, maybe even some completing the squares. Thanks for watching.